Welcome to the next talk, student seminar, which will be given by Michal, and it will be about boundary terms and their structure in Euclidean teleparallel gravity.
All right. First of all, thanks for the nice introduction. And second of all, thank you for this opportunity to talk to you a bit about, well, as has been already mentioned, about the gravitational action of black holes. But we will not be interested only in the action within the standard general relativity. We'll be also interested in the action integrals in its teleparallel formulation. Okay, so with regards to the structure of today's talk, I've decided to break it down into three separate parts. In the first part, I will present you with a basic geometrical background and hopefully also some geometrical intuition that will prove hopefully helpful in what's coming next. In the second part, I will present the standard derivation of the black hole action following the Gibbons-Hawking-York method within GR. And lastly, we'll focus on the main topic of today's talk, and that will be the evaluation of the black hole action within its teleparallel formulation. Okay, so the geometrical background. That's it. All right, so it turns out that in general teleparallel gravity, it's most natural to use the language of tetrads. So what are the tetrads? It turns out that tetrads allow for a very straightforward generalization of coordinate bases into non-coordinate bases. And they are simply defined as a set of four orthonormal vectors. And the defining property of tetrads turns out to be this non-trivial commutator of two tetrad fields, which turns out to be proportional to the coefficients of anholonomy, in this case denoted by FCAB. And in general, these anholonomy coefficients are non-trivial only for non-coordinate bases, and therefore they are sometimes referred to as anholonomic bases. On the other hand, the coordinate bases, sometimes referred to as holonomic, they have very trivial commutators since the coordinate bases are given in terms of the partial derivatives, which trivially commute. Therefore, also its commutator will turn out trivial. Well, okay, so on the account of orthonormality, this is achieved by fixing the metric in the tangent space to be Minkowski, and in the Cartesian coordinates given in terms of this mostly plus convention. And what it does, it allows us to write the space-time metric G mu nu in terms of the tetrad fields, and this presents us with a one-to-one correspondence. So how this expression works is that once you give me a space-time metric, which is denoted by these Greek indices, you can automatically read off the form of the tetrads. And from the other viewpoint, if you give me a tetrad, I can contract two tetrads with the Minkowski tangent space metric, and in this way we obtain the space-time metric G mu nu. Okay, so as we aim to derive a theory of gravity in within teleparallel geometry, it turns out that covariant derivative will prove to be crucial in our endeavors, and therefore, as we've been talking about two kinds of bases, we need to specify how this covariant derivative acts on these two types of bases. Okay, so it turns out that in the case of components of tensors, with respect to the coordinate basis, we define the action of the covariant derivative in terms of coefficients, in terms of connection coefficients, denoted by gamma. And on the other hand, when we act with covariant derivative on components of vectors with respect to the non-coordinate basis, which are denoted by these Latin indices, we define the action in terms of what is usually referred to as a spin connection. Okay, but once we realize that these are merely two kinds of connection coefficients for the same connection, in this case, I've decided to denote this general connection by this bolted nabla. We want to, okay, so after we realize that these are merely two kinds of connections for the two kinds of connection coefficients for the same affine connection, however, written only in two separate bases, well, once we realize that action of the covariant derivative on a tensor as a standalone object should not depend on the choice of the basis, we get a straightforward relation between these two kinds of connection coefficients in this final relation. Okay, so far we have been working in this very general formulation of geometry, sometimes which is sometimes called as metric affine approach to geometry. And turns out that all of the important information can be encoded in three types of tensors. And in turn, demanding some conditions on these tensors will lead to some specification for the particular form of these connection coefficients. So it turns out that in the case of coordinate basis, it's most natural to use a pair of variables in terms of the spacetime metric g mu nu and the connection coefficients gamma. And in this way, we define following three tensors. Firstly, we define the standard Riemannian curvature tensor. In the second line, we define the torsion tensor. And in the last line, we define what is sometimes called as non-metricity tensor. On the other hand, when we work in the non-coordinate basis, it's much more natural to use tetrads and spin connection. And I've also written down the corresponding expressions for the components of already mentioned tensors. Sorry. Okay, so what you can do now is you can play this very, very straightforward game, and that is, as we want to obtain a. Okay, so in the case that we want to obtain the standard Riemannian, or sometimes it's called Levi-Civita connection, and hence I've decided to abbreviate this as an RLC connection. We obtain this specific form by demanding the torsion vector and non-metricity tensor to vanish, and this leads to a unique expression for the connection coefficients. In this case, we usually call them Christoffel symbols, and as you can see, in this case, these are precisely given in terms of the metric, the spacetime metric. At the same time, you can also express the connection coefficients with respect to the non-coordinate basis within the Levi-Civita connection. And in such a case, it turns out that the spin connection will be given in terms of the coefficients of anholonomy. Okay, so, well, this was when I was firstly presented with this Levi-Civita connection, a very natural question immediately popped up, and that is, why do we actually need to consider vanishing torsion and non-metricity? I mean, at least the non-metricity condition, the metric compatibility, is somehow very natural. You want to preserve the scalar products of vectors along parallel transport. However, the condition of vanishing torsion is, I would say, rather ad hoc, so I was immediately prone to ask the question whether we can actually relax this condition and what would be the consequences of this. And it turns out that once you decide to let the curvature tensor vanish and you leave the torsion non-vanishing, in this case you end up with what is called as a teleparallel connection, and the first condition of vanishing curvature is solved precisely by the spin connection of the pure gauge form. Okay, so why is it sometimes called pure gauge? That's simply because if you recall the transformation law for the spin connection, in general, there will be a homogeneous piece which transforms covariantly. Okay, so let me just write down some expressions. Okay, so the usually transformation law for spin connection, as I've said, features this homogeneous term. So in the case of non-coordinate bases, we transform the frames by local Lorentz transformations. Therefore, this homogeneous piece will turn out to be as lambda AC. Here we need to put C, D, mu, lambda, BD. And then there will pop up this inhomogeneous term, which is proportional to lambda d lambda, basically. Lambda AC, okay, let's write it like this. Okay, so what it means that we have a spin connection of a pure gauge form is that we simply work with a spin connection which is in some preferred frame equal to 0, and then in any other Lorentz transform frame we inevitably obtain spin connection of that particular form. Okay, and it turns out that very crucial relation will be the decomposition of stellar parallel spin connection into the Levi-Civita spin connection. Oh, by the way, I denote objects with respect to Levi-Civita connection with this little circle on top of them. And it turns out that the parallel connection can be decomposed into RLC connection plus what is sometimes called as contortion tensor, which is just a linear combination of torsion tensor. Okay, so hopefully now we get a nice understanding about the geometrical background behind teleparallel geometry. And now let us head into the derivation of the black hole action within general relativity. Okay, so as has been mentioned in the introduction to this talk, we'll be interested in finite non-zero solutions to the Euclidean action. And why is it important? Well, it turns out that these finite solutions are crucial when it comes to the path integral approach to the black hole thermodynamics. In such a case, we usually define the partition functions in terms of the path integral as follows, where there's this pesky, highly oscillating functional there, and as we want to eventually evaluate this this path integral, what is usually done is that we undergo a weak rotation to turn this badly oscillating integral into a, well, let's say a damped integral, which in the semi-classical approximation can be approximated as simply the value of the Euclidean action on shell. Okay, so as we want to evaluate these Euclidean actions for the Schwarzschild black hole, recall that Schwarzschild solution is a vacuum solution. So if you were to use the standalone Einstein-Hilbert action, you would recover a very trivial result, because for vacuum solutions, the Ricci tensor is equal to 0. Therefore, if we want to obtain some non-trivial results, we need to somehow modify the action, or at least we need to add some non-trivial terms. Okay, so to see how we can actually modify this action, let us firstly recall the variation of the standard Einstein-Hilbert action, where we obtain these two terms. The first term is proportional to the Einstein tensor, leads to the universal of Einstein field equations. However, there is also this second problematic term proportional to the variations of the Ricci tensor. And what is sometimes done at the lectures for general relativity is that we, along with assuming Dirichlet boundary conditions, that is, by fixing the variations of the metric on the boundary, we also fix the variations of the derivatives of the metric at the boundary at the same time, which is, however, inconsistent in the case when our spacetimes feature natural boundaries, for example, horizons. Okay, so how do we handle this pesky term? So usually what we do is that we use this what is called Palatini identity, which allows us to transform the variation of the Ricci tensor into a total divergence term. And once we see a total divergence term, we automatically want to transform it into a total derivative term by this very useful formula, prescription. And then we use the Stokes theorem to transform this total derivative term into a boundary term. Okay, so if we substitute back, if we substitute in for so if we substitute back in for the values of variations of the Ricci tensor, what we find out is the following boundary term given in terms of the variations of the partial derivatives of the metric. And since we want to have a consistent variational principle, we somehow need to compensate for this unwanted term, and the way it is usually done, we add this term, which has precisely the same structure as this unwanted term. However, it is with a opposite sign, which precisely cancels out this unwanted term. All right. Okay. Okay, and also notice that we can actually rewrite this expression in terms of what is called the extrinsic curvature, or rather its trace. And therefore, the overall corrected action of general relativity turns out to be corrected by this boundary term proportional to the extrinsic curvature. However, this is not our final form of the action we want to work with, because it turns out that in the case of asymptotically flat spacetimes, these actions, given in terms of the Gibbons-Hawking-York boundary term only, suffers from infrared divergences. That means that at large values of at asymptotic infinity, there are usually unwanted divergences, and as we want to obtain a finite result, we need to undergo some sort of regularization. And well, in the case of Gibbons-Hawking-York boundary term, it turns out that this trick can be carried out by what is called the background subtraction, which essentially amounts to calculating the extrinsic curvature for the flat background. It's nothing more, nothing less. You simply look at the value of the metric at asymptotic infinity, and then you construct the extrinsic curvature out of it, and this should, in principle, regularize the action so that we obtain a finite result. Okay, so as I've been advertising, we want to evaluate Euclidean actions, and therefore we need to firstly present you with the Euclidean Schwarzschild solution. And so the standard Lorentzian Schwarzschild metric can be written like this, where we have opted to parameterize it in terms of this function f squared, unlike usual f. And it turns out that we can analytically continue this solution into a Euclidean one by the means of Wick rotation. So this is, I will sometimes refer to this Wick rotation as a coordinate Wick rotation, because all it entails is that we substitute the temporal coordinate by the stall coordinate, which is just I times t. Okay, and in this way, what it essentially does is it flips the sign in this G total component, so that we manifestly obtain a Euclidean form of the Schwarzschild solution. However, undergoing this Wick rotation causes our temporal coordinate to become compactified. And therefore, we need to specify its period. And it turns out that in this case, we need to specify the period to be precisely 8 pi m, which is the inverse of the Hawking temperature. And in this way, our Euclidean Schwarzschild solution won't feature any coordinate singularities at the horizon. Okay, so topologically, one can imagine the Euclidean Schwarzschild solution to look like a semi-infinite cigar. I mean, instead of thinking of a Minkowski spacetime, we now need to think in terms of this compactified time coordinate. And what is important here is that in this way, we only cover the exterior region of the black hole. And what we aim to do eventually is that as we want to evaluate the boundary integrals, we need to specify a hypersurface of some sort. And in this case, it's most natural to use hypersurface of constant radial coordinate. And then we send this radial coordinate all the way to infinity. And hopefully, this should encompass all of the space-time. And therefore, our solutions should be somehow unique. Okay, so now let me just reiterate what I just said. So as we want to evaluate the boundary integral, we firstly set the hypersurface of constant radial coordinate, and then we send it all the way to infinity. Okay, so first what we need to do is we need to specify a normal vector to this hypersurface, from which we can automatically calculate the trace of the extrinsic curvature. Lastly, we look at the asymptotic values of the metric at the radial infinity, and from that we can specify the form of the extrinsic curvature for the flat background. Also notice that in this case the form of the Jacobian will be somehow different from the usual one we are used to in Schwarzschild. In standard Schwarzschild solution, but nevertheless this is the correct answer. Okay, so as I've been talking, we would like to express the exterior solution for the black hole, Euclidean black hole, and putting all of these things together leads to this universal, very famous result of Gibbons and Hawking. And it turns out that this boundary action is equal to the beta m half, where beta is the periodicity of the new compactified coordinate. Okay, so from the knowledge of the Euclidean GR action, we can then go on and specify the value of the partition function following the semi-classical approximation. And from that, we can finally find or rather specify the entropy for the black hole, which is given in terms of the mean, in terms of the free mean energy, and plus this logarithm of the partition function. Okay, all in all, it turns out that in following this Euclidean path integral approach, we recover the standard Bekenstein law for black hole entropy, which is area over 4. Okay, so now we are heading into the last section of today's talk, and that will be on the topic of teleparallel gravity. Okay. All right, so first of all, we need to specify the form of the teleparallel action that we are going to use throughout the rest of the talk. And it turns out that all we need to do is to apply this spin decomposition I've written down on the blackboard. And once we apply it to the Ricci scalar, it turns out that it decomposes in this very nice way, where we have defined the torsion scalar implicitly as a linear combination quadratic intorsion tensor. And now it is very natural to consider the teleparallel action to be just given as a volume integral over this torsion scalar, right? If we do this, we can immediately see that the teleparallel action will be dynamically equivalent to the GR action because it's equivalent up to a total derivative term. And we all know that total derivative terms do not contribute to the field equations. Okay, another way to see it is that once we vary the teleparallel action with respect to the dynamical variable, which is in this case the tetrad, we obtain field equations which are completely equivalent to the GR equations. Also notice that already at this level, we can say that this Euler-Lagrange expression for the field equations is, in the case of GR, symmetric, and therefore also in teleparallel gravity, these field equations only fix the 10 components of tetrad, and well, let's just say that tetrads are not neither symmetric nor antisymmetric, so they are given in terms of total of 16 components. So the additional 6 unconstrained degrees of freedom are related to our freedom in local Lorentz transformations. And these should not be dynamical. So it turns out that very similar thing holds also for the teleparallel spin connection, which is a priori assumed to be dynamical, just like the tetrads. But however, when we decompose the teleparallel Lagrangian as a function of both the tetrad and the spin connection, it turns out that all of the dependence on the spin connection is given in terms of total derivative term. And yet again, total derivative terms do not contribute to the dynamics. Therefore, we will obtain no additional field equations, which would help us specify the form of the spin connection. And well, what it means is that with regards to the dynamics, we may just as well use vanishing spin connection and nothing really bad happens. I mean, it seems rather advantageous over GR, because in GR, if you want to study, for example, motion of particles, besides solving the field equations for the metric, you then need to go out and calculate the Christoffel symbols, and everything else follows straightforwardly from there. However, in teleparallel gravity, when we are interested in dynamics, we just need to know the form of the tetrad, and we may just work with a vanishing spin connection. Okay? The problematic part is that we want to evaluate the action. Therefore, it turns out problematic to work with an arbitrary connection, because just like in the case of GR, and just like when we assume the inclusion of the Gibbons-Hawking-York boundary term, it turns out that these teleparallel actions usually suffer from the same divergences as in GR. Therefore, we need to somehow specify the form of the spin connection to hopefully regularize these actions. And the way it is usually done, as has been realized by Kershak and Pereira in 2015, is that we specify the form of our teleparallel spin connection as the Levi-Civita connection of the reference frame. Okay, so what is the reference frame? First of all, reference frame is defined formally as a reference frame when the gravity is switched off. So what it means that, well, recalling this spin decomposition relation, if we assume that we are working in a flat space, that is, we are working with in a reference frame where the gravity is switched off, the contortion piece, which is proportional torsion tensor, will vanish, because for flat connections or flat spacetimes, not only does the curvature tensor vanish, but also the torsion tensor vanishes, and also the non-metricity. Therefore, for these reference frames in the flat case, this second piece will drop down altogether, and what we will be left with is precisely what is written down here. Okay, and it turns out that this is equivalent to demanding a sufficiently strong fall-off for the Lagrangian at radial infinity. Okay, so now before we head into the actual evaluation of teleparallel actions, we need to firstly think a bit more about how to undergo the weak rotation in the case of tetrad formalism. So the way we have decided to do it is, well, first of all, it turns out that we've got two options now. Recalling the perennial expression for tetrads in terms of the space-time metric, and now let's assume we are working in a flat space-time. Let's just write down the left-hand side of of the original expression to be given in terms of the Minkowski spacetime metric eta mu nu. On the right-hand side, we just write down the usual expression for tetrads, given as eta AB, whatever. Okay, so the Vig rotation, what it does is that on the side of the spacetime metric, coordinate Vig rotation by assuming our new temporal coordinate tau, given like I times t, causes the spacetime Minkowski metric to turn out as a standard Kronecker delta mu nu. Because here the spacetime Minkowski metric is given just as minus plus plus plus. Well, undergoing the Vig rotation will cause the TT component to become positive. So here, well, I hope you can see it actually, but here delta mu nu will be just plus, 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 and plus. And on the right-hand side, well, we don't actually need to modify the form of the tetrads in any way. All we need to do is do the Vig rotation for the tangent space Minkowski metric. So all we need to do is to just substitute for the Minkowski eta AB metric. We just substitute the Kronecker delta AB here. And we can continue, in principle, we can continue using the tetrads just like before. Okay, so in the case of flat spacetime, it seems that to undergo a Vig rotation in the case of tetrad formalism, all we need to do is to substitute the tangent space Minkowski metric for the Euclidean counterpart. However, it turns out that this approach is not really consistent because, well, let me just demonstrate this on a particular cases, and hopefully we shall see what's so problematic. Okay, so heading into the first case, we're going to be interested now in what's usually called as a diagonal frame or diagonal tetrad, which is read off very easily from the spacetime metric written in Schwarzschild coordinates. It's just basically square root of the metric. Okay, so as I have already said, in case of teleparallel gravity, we need to specify the form of the spin connection. And the way it is done is that we need to firstly specify the reference frame or the reference tetrad. And in this case, it's very easy to see that doing the limit as r goes to infinity, our diagonal frame will recover the Minkowski frame in spherical coordinates. From the knowledge of this reference frame, we can then go on and evaluate the non-trivial components of the spin connection, and utilizing all of these things, we are now able to evaluate the action itself. So in the case of teleparallel bulk action, which is given in terms of the torsion scalar, we obtain the value for the black hole action to be beta m. Therefore, we arrive at the first ambiguity within this teleparallel approach, and that is the bulk teleparallel action leads to twice the value obtained by the Gibbons-Hawking method. Okay, but recall our expression at the first slide that we started with. Well, let's just say that in this view, what we can do with that is that instead of working with a bulk teleparallel action, what we can do is that we can work instead with this additional right-hand side, and more precisely with this additional total derivative term, because just like in GR, for the flat space, for vacuum solutions, this Ricci scalar will vanish trivially. Therefore, it seems that in teleparallel gravity, we really do have two options to evaluate the action, and that is either by the bulk teleparallel action, which is an integral over a space-time volume, or we can do the we can transform the total derivative term into a boundary term, and therefore we got this other approach. We can evaluate the teleparallel action. So just like in the case of Gibbons and Hawking, in order to evaluate the boundary integral, we need to set up the hypersurface. So just like before, it's set up as some constant radial coordinate. And well, evaluating the torsion vector, turns out that in this case, we recover the same result just like in the case of Gibbons and Hawking. Okay, so far, it seems that albeit we have two approaches to evaluating the Euclidean teleparallel action, that is, we either evaluate it volumetrically or we evaluate it quasi-locally, it turns out that these two approaches are not really consistent at this level. Okay, so this is actually the original problem we have started with. And then we went on to investigate what is going on in here. And well, let's just say, yeah, okay. So what we have found in the literature is that assuming what is called the canonical frame, it was argued by Tommy Koivisto in 2019 and their collaborators, is that these canonical frames will lead to a unique finite result for the action. Well, okay, so what is the canonical frame? It turns out that the canonical frame can be defined by a rather straightforward condition of vanishing of the energy momentum pseudotensor. And luckily for us, there's a whole class of metrics which fulfill these conditions, and these can be found within the so-called Kerchild class of metrics. Okay, so Kerchild class can be written as follows. We decompose the spacetime metric into a flat Minkowski metric plus this additional term quadratic in null vectors. In the case of Schwarzschild, where we have no rotation, this function f turns out to be just m over r. And well, if we know the form of the metric, we can therefore straightforwardly read off the form of the tetrad. Okay, so however, it turns out that undergoing the Wig rotation, in this case, turns out to be problematic. Why is that? Well, it's quite easy actually, because in the case of Euclidean signature, there's no well-defined notion of null vectors. I mean, how can you obtain a zero scalar product with a positive definite metric? Therefore, we needed to somehow circumvent this problem. And the way we have done it is that we firstly looked at the spacetime metric, which in this case, the Kerchild ansatz leads us to a Schwarzschild solution written in terms of the Einstein, in terms of the Eddington-Finkelstein coordinates, and we undergone the coordinate Wig rotation. However, there's a big problem, because in the Eddington-Finkelstein coordinates, there's this pesky cross term present. And when you do the standard coordinate Wig rotation by substituting t for tau, well, this unwanted cross term will inevitably lead to our metric becoming manifestly complex. And let's just say that complex metrics, well, we are not really used to those. We can't really handle them all that well, but let's just say at this level that it's completely normal. Once you are using non-static coordinates, you will inevitably obtain a complex metric once you do the naive coordinate Wig rotation. And once we've done it, you can therefore use this relation, and you can then read off the form of the tetrad, which will also, in this case, turn out to be complex. Okay, so having all of these things in mind, we are now ready to calculate the teleparallel action. But what is rather strange is that it turns out that in the case of the bulk teleparallel action, we obtain a trivial result. Turns out that in the case of canonical frame, there's simply no action to be evaluated. On the other hand, recall that we have two options to evaluate the action teleparallel gravity, and that is we may instead of evaluating the bulk integral, we may focus on the boundary integral. So just like before, we look at the components of the vector torsion, which in this case looks like this. And then we calculate the boundary action, which turns out to recover yet again our Gibbons-Hawking-York value. So far, what we can say is that, well, you absolutely cannot trust the values you obtain following the bulk teleparallel action. But it seems that so far, this other quasi-local approach has been really consistent. This is what you actually need to do when you try to evaluate these actions in teleparallel gravity. You just simply need to do it just like in GR, and that is, you need to calculate the boundary integrals. However, these two actions should be equivalent, and well, how can 0 be equal to m½ or beta m²? So we were really like, we were not okay with these results, so we were trying to investigate a bit more. And let's just say that lastly, we'll consider this third type of frames, sometimes referred to as free-falling frames, and they are simply obtained from the diagonal frame, which we have started with, by a radial Lorentzian boost in the radial direction with the rapidity of square root of 2m/r. In this way, we may view these free-falling tetrads as free-falling observers, and therefore we naturally think that also the torsion scalar will turn out to vanish, because locally free-falling observers should not see any gravitational effects. However, it also, just like in the case of canonical frame, just simply undergoing the tangent space Vig rotation doesn't lead to consistent results. Actually, if you were to use this Lorentzian version of canonical frame, what you would end up with is the same result as we are aiming to evaluate now, but there would be a flip sign, which we do not really understand. I mean, how can you have black holes of negative mass, whatever? So what you do is just like in the case of canonical frame, you firstly Vig rotate the space-time metric, which is in this case given in terms of the so-called Painlevé-Goulstrand coordinates. And well, just like in the previous case, since these coordinates are not static, there will be this pesky cross term present in the metric, and undergoing the Vig rotation will inevitably cause it to be complex, and therefore also reading of the adopted tetrad, it will turn out to be complex as well. Okay, so what you can, so how you can actually obtain this frame is there's a alternative way to obtain this frame. So if you think back and realize that obtaining the free-falling frame is just, all you need to do is to just use the Lorentzian boost on the diagonal frame, well, then it makes sense to obtain this frame within the Euclidean formulation, not by a Lorentzian boost, but you should obtain it via Euclidean analog of the Lorentzian boost, which we have decided, or I have decided to be precise, to parameterize this Euclidean rotation in terms of parameter alpha, which was found to be given in terms of arc cosinus of 1/f. And well, let's just say that applying this Euclidean rotation to our original diagonal frame will recover precisely this complex form of the tetrad. Okay, so well, evaluating the bulk integral is trivial because torsion scalar vanishes. However, we have this other option of evaluating the action quasi-locally. Therefore, we inspect firstly the torsion vector, and what we find out that the radial component is now thrice the value as in the case of canonical frame, and therefore also the overall teleparallel action
following the quasi-local approach turns out to be thrice the value obtained following the Gibbs-Hawking-York method. Okay, so what the actual hell is going on? I mean, so far it seemed like we can't trust the bulk integrals, but the boundary terms should be fine. And now in these in these weird Euclidean free-falling frames, it seems like the value is not universal. And well, let's just say at this point, all we can state is that it turns out that in parallel gravity, the value of the black hole action might be frame dependent. Now, if you think about it carefully, it seems that what is really causing this problematic behavior is our Euclidean rotation. So this is what is actually responsible for this additional factor of 3. Well, what would prevent us to act with this Euclidean rotation multiple times? I mean, you can do it as many times as you want. So let us define the nth application of the Euclidean rotation on our original diagonal frame like this. And then we expect the radial components of torsion vector for each of the applications of the Euclidean rotation. And it turns out that in this way, we obtain a recurrent formula for the torsion vector. And it leads us to this following expression for the boundary action of free falling frame in terms of the value of, in terms of the number of applications you have used the Euclidean rotation for the diagonal frame. So not only is the action not unique in teleparallel gravity, but it seems that you obtain an infinite number of actions for the black holes within teleparallel gravity. And I mean, okay, so what is going on? So let me just summarize what we've been talking about so far. Okay, so in teleparallel gravity, we asserted the equivalence to GR up to a boundary term. Okay, in this way, we obtain a theory that was equivalent to GR at the level of dynamics. However, as we all know, evaluating the action is not that simple, and we need to really take care of these total derivative terms properly. It turned out that the teleparallel boundary term structure exhibited much richer structure than in the case of the Gibbons-Hawking-York boundary term. And what is even less okay is that the bulk action approach was not consistent even within one frame. So if I were to point my fingers at one sole perpetrator of this weird behavior, I would say that it was our use of the inertial spin connection. Why is it so? And how can we actually view that this use might be problematic? The first instance where we can look at the problematic behavior of inertial spin connection is that, well, let's just say that objects constructed from teleparallel spin connection should transform covariantly. However, we've seen that in the case of the diagonal frame, we obtain the value for the torsion scalar to be beta m once we have integrated. But however, in the case of canonical frame, our torsion scalar turns out to be vanishing. So if it is truly a scalar, and if it vanishes in one frame, it should be 0 in any other Lorentz transform frame, right? That's what it means to be a scalar. It should not change when it's vanishing in one frame. Therefore, we see that our spin connection doesn't actually provide us with tensorial quantities. And moreover, it turns out that our spin connection in this case regularized this action all too well. We obtained finite result, however, it was trivial. And in order to obtain non-trivial results, well, we needed to resort to the boundary terms. Okay, so what to make what to make of all of these results? Well, we can ask the question whether the Euclidean teleparallel action is indeed frame independent or dependent. Depending on the answer, if we take these results as something, oh no, if we take these results, I mean this infinite tower for the values of the black hole action, to be correct, well, then we need to somehow specify what is the black hole thermodynamics now. Because as we have seen, our black hole, or the black hole entropy was given in terms of the free mean energy. And then there was this partition function, which was proportional to the Euclidean action. And now, as unlike in GR, where we had a unique result of beta m half, we were able to obtain the Bekenstein law for the entropy. But now in teleparallel gravity, we have an infinite value for the action of the black hole. And if we were to modify, I mean, if we assume that these values are really non-trivial, well, then it means automatically that the entropy for the black hole is not really universal. It's not given only as an area over 4. Okay, so this is the first problem we would need to think about. And secondly, this might prove somehow problematic when it comes to the quantization of gravity, following the black hole thermodynamics. And if we actually demand that the teleparallel action should really be frame independent, therefore we would like to discard all of these results, well, my view is that we need to somehow specify the spin connection with teleparallel gravity in some other manner that we have used now. Therefore, we might consider, for example, some sorts of holographic renormalization, or we may start to exploit the remnant symmetries, and I don't know what else. So that's it from my side, and I guess thank you for the attention. Any questions? Everything's clear?
Yeah. So if you add this boundary term to the action, does that modify the boundary quantities such as energy, mass?
Yeah, that's the tricky part. I mean, because, well, so far it seemed like the value of the mean energy is somehow given. It's fixed. It's equal to m. But it might turn out that in teleparallel gravity, just like we have been able to modify the values for the action, it may turn out that in teleparallel gravity, we also need to change the value of the mean free energy. And these two sorts of behavior might somehow cancel out, and we might in the end end up with this universal Bekenstein law for entropy of the black holes. But I don't really know. I have not really studied thermodynamics within teleparallel gravity. But yeah, there's definitely much more work to be done.
What's the meaning of this strange Wick rotation? Because like, shouldn't Wick rotation done twice return you back to time? Why is it? Like, why? How can you call this a Wick rotation if, when you apply it multiple times, it gives you something else?
By applying these Euclidean rotations, well, you should not really view this Euclidean rotation to be responsible for the Wick rotation per se. All I'm trying to say here is that if you want to obtain Euclidean analog of the free-falling frame, this is the transformation you need to do on the diagonal frame in order to obtain it. In order to obtain a solution to the Euclidean field, Einstein field equations. If you actually, well, just like I've said before, if you try to use the Lorentzian version of the free-falling frame and you just undergone the big rotation in tangent space, well, let's just say that on the left-hand side where you have the space-time metric, you would not obtain the same result by the coordinate with rotation on this side and just by the tangent space with rotation on the other. Those two metrics wouldn't match. And well, this is actually responsible for the opposite sign if you were to evaluate these actions. Unlike in the Lorentzian case where you have only one option, in the Lorentzian case, this is the one and only frame you can consider. In the Euclidean version, due to this ambiguity of how to undergo the big rotation in the tangent space, you sometimes have these additional weird complex tetrads, but you also have their counterparts that lead to opposite results. I don't know why is that so, but so far we've agreed to simply disregard those weird solutions as not physically relevant.
That sounds like you just basically can't even hope to think to be able to calculate anything like the action, right? If it's just badly defined, then it's badly defined.
Well, let's just say that it's badly defined within this one frame. In the other frames, the result was somehow consistent. But yeah, I mean, what to make of it, I don't really know as of now. Any other questions?
I guess that's all.
Okay, thank you.